Okay. Let's get started. Thanks so much for joining us today. Today we're going to be talking about adaptive bitrate logic, and especially on the player side, and how it can really help you make or break a quality of experience for viewers. Give you a little bit of background on us. My name is Erica. I'm heading partnerships at StreamRoot, and I'm joined by one of our founders and our CPO, Nikolai Radionov. StreamRoot has developed basically a delivery optimization technology, a peer-accelerated OTT delivery optimization technology to help broadcasters overcome some of those challenges of quality, of offering high-quality video at scale at an acceptable cost. So our core technology, which we call StreamRoot DNA, distributed network architecture, is essentially an intelligent distributed network that multi-sources content from both a mesh network of viewers and traditional CDN. So we have integrated our solution. Our solution is actually integrated on the player side. We interact with the player's ABR algorithms. So we've had a lot of experience in the course of our research and in the course of our large-scale deployments with several of our customers to kind of look into the inner workings of how HTML5 players work, how they handle their adaptive bitrate logic, and how they do it and what they could be doing better and what they do well. So this is a subject that we know quite well and that we like to talk about. So to give you an idea of exactly what we'll be talking about today, I'm going to be kicking off with just a kind of general overview of how ABR works and the design goals, how we design these types of algorithms, and what trade-offs and parameters must be taken into account by the player when creating and building one of these types of algorithms. We'll then be looking a little bit more in depth on the building blocks of what we would call a bandwidth-based ABR algorithms, so the parameters that the player takes into account, and the different constraints and processes that the player goes through to pick the best bit rate possible and to offer the best quality of service. Nikolai is then going to take a couple examples of two of the open source players that we have been working on quite often, and how these handle the adaptation logic. In the third part, we'll give kind of a little introduction to buffer level-based algorithm and how this type of algorithm would work in addition to a bandwidth-based algorithm, again, using an example to illustrate these principles. And then in the kind of maybe last third of the presentation, we wanted to give you an actual real-life example of one of our customers, Dailymotion, that was able to actually materially improve their quality of service in just a few weeks of tweaking their ABR. So we have some stats that Dailymotion has let us use. We're very appreciative of that. And we'll look at exactly what they were able to do just by tweaking their player. And then we'll finish up by looking a little bit at what you can do to tweak your adaptive bitrate algorithms and what to keep in mind when trying to tweak your player. So let's start out with just the basic design goals, and maybe even before that, why ABR? I think we all know that HTTP streaming has become the standard today and has basically brought about two fundamental changes in the way in which we manage streaming in general. The first being, now we're taking into account varying network conditions and a multitude of different devices and different resolutions that we could be streaming on. And to do so, we have essentially divided video into discrete chunks of fixed duration and encoded them at several different bit rates. So we have several different bit rates to choose from. And at the same time, we've shifted away from proprietary transport protocols such as RTMP to an HTTP TCP stack. So this has kind of created a sort of layering effect and a degree of removal for the player and from the actual transport conditions. So now we're actually going to have to more estimate what the actual underlying network conditions actually are. So in terms of design goals, when designing an ABR algorithm, we want to make sure we're obviously optimizing viewer quality of experience. And to do so, we need to balance, I would say, three main criteria. The first one is to maximize efficiency. or to maximize bit rate. We want to design a system such that the viewer is always streaming at the highest resolution possible for the bandwidth available. And so the metric that we use on that is the bit rate. We then want to minimize rebuffering. We want to make sure that we're actually effectively fetching and storing chunks before rendering them on the screen, and that we have kind of a buffer that allows us to not harm playback in the case of a sudden drop in network conditions. So this is quantified. We quantify this as the buffer size. And then the third condition the third criteria is to limit or encourage stability. We want to limit, to the extent possible, the number of track switches, which can be perceived as quite annoying. For a more seamless viewing experience, we don't want to be switching bit rates all the time. So we want to have a seamless, smooth experience, encouraging stability. There is a fourth criteria that I've put on here that is not necessarily the subject of the presentation today and is not really taken into account by most ABR algorithms that are actually used in production. But I put it on there because it is something that is present in a lot of the research that's being done into improvements on ABR, and that's to promote fairness across network bottlenecks. What we've seen is that most of the algorithms that we have do not necessarily lead to a fair allocation of bandwidth resources, and a lot of the research that we've seen is taking this into account as a primary design goal. We're not going to talk a lot about it today. I just wanted you to be aware that exists as well. So let's look at how this actually works within the player. To start out, we've basically divided the two kinds of metrics into two different categories. The first category is what we call constraints. And constraints, hierarchically speaking, tend to supersede the logic of the other algorithms and most often act as a control mechanism when the player is either starting up or in the event of a sudden drop in or change to the player's environment. So these include screen size, dropped frames, and startup time. Not an exhaustive list, but these are kind of the three that we've picked out to talk about today. The second category that we've identified is the parameters or trade-off parameters, and these are basically what is at the core of that maximization problem that we're trying to achieve in designing an ABR algorithm. So we have the size of the buffer, we have our bandwidth estimation, and then as kind of a bonus, we're going to be talking a little bit about how we at StreamRoot actually handle the bandwidth estimation when we have actual video segments coming from various sources, not just the CDN, because there's an extra logic that we actually have to use for that. Let's take a look at these in a little bit more detail. So in terms of constraints, we have screen size and player size. This one's pretty simple. We don't want to be streaming on a resolution that is larger than your actual player size or your screen size, because it's essentially a waste of CPU and resources to actually have to recompress the video in order to render it on the screen. So a good algorithm is going to take that into account. It's going to detect the player size. It's going to cap the bit rate at a certain amount, and not try to stream on a bit rate that's a resolution that's larger than the player size. Obviously, the player size can change if we are going into full screen, for example. So this is something that needs to be checked dynamically. Secondly, we have the drop frame rate. And this is basically if the device does not have enough resources, what we're going to start doing is dropping frames. We're not going to be able to decode the frames quickly enough, so the device is going to start dropping frames. And past a certain point, this actually is perceptible by the user and quite annoying. So what the player can do is basically calculate the number of frames that have not been decoded because of lack of time compared to the number of frames that are decoded, and then construct a rule and construct a rule accordingly. You can ban a certain bit rate if you know that the device just simply can't handle it. And we'll see that in an example. And then the third constraint that we've identified is startup time. This will depend largely on your use case, but as a general rule, we want startup time to be as short as possible. Many algorithms begin downloading the first segment or segments at the lowest bit rate possible in order to achieve that quick startup time. However, we also want the player to be able to ramp up to the correct bit rate pretty quickly. We don't want to have someone streaming on the lowest bit rate for 30 seconds just because the player wanted a quick startup time. So we want something that is also going to ramp up aggressively. So that's also something that the player can take into consideration and can be constructed such that it will do that. So this is not an exhaustive list. Things like device, mobile versus Wi-Fi network, et cetera, are also important to take into consideration. But these are the ones that we'll see in our examples today. Now moving on to kind of the most fundamental part of the ABR algorithm, we have to estimate the available bandwidth to the player in order to know which bit rate we should be streaming on. And so this is the most important part of the ABR algorithm and is the most difficult to get right, as it essentially involves trying to both maximize the bit rate that we're streaming on and also minimize rebuffering. So the simplest of algorithms, what we see is quite simply the simple algorithms that we've seen. Essentially calculate this by seeing how long the last segment took to download. So we're taking the download rate of just the last segment, the size of the segment divided by the time that it took to download, and we're going to say that that's our bandwidth that's available, and we're going to use that to get to the next to determine which bit rate we should be streaming on for the next segment. This simple approach can work in production, and several players are actually using this in production. However, as you can imagine, the download time of the last segment is not always a very accurate representation of the network conditions right now, and especially if you have a highly variable network. What we see is it tends to kind of like oscillate. The bit rate oscillates a lot if we have a variable network and we're only using the last segment or couple segments. And so this obviously leads to inconsistencies, and it leads to a lot of track switching. And that's something that in the beginning, as we said, one of the design goals is to kind of smooth the experience as much as possible and not have a lot of track switches. So several a little bit more complex algorithms have been put in place and to try to really achieve that maximum bit rate, but also better stability and fewer track switches. So first off, instead of just taking the last segment into account, we're going to start taking historical values into account to see those historical patterns. So we're going to take the last 5 seconds or the last 10 segments or whatever, basically. And we're going to try to smooth that, essentially. After taking these historical values into account, we then apply a smoothing function that basically allows us to average them out and to kind of get rid of any outliers. They're going to bias the calculation. For the smoothing function, there are several possible averages that can be used. It will probably depend on your use case, what you want to be using. For example, in live streaming, we want to be extremely reactive to downward changes in bandwidth in order to not have rebuffering. We also want to be more conservative to upward changes because we don't necessarily want to be always on the highest bit rate because it will probably cause a switch down at some point if your throughput is really not very, very stable. So just take into account at this point, the stronger the filtering of that smoothing function, the less reactive the player is going to be to sudden changes in bandwidth. We're going to see a couple examples of what kind of averages are used. The next step would be quantizing. After smoothing the values, we might also want to apply a coefficient in order to kind of, again, avoid the effects of sudden and short-lived changes in network conditions. And again, as a general rule, we want to be more conservative when switching up, more aggressive when switching down. So there's a final step to this, actually, and that's the kind of to schedule the download step. And for that, we can switch over basically to our buffer. And what the buffer can do in this case, and one thing that's interesting, the buffer can actually override some of the bandwidth estimation rules in the event that there is a sudden change in network conditions and we're in the middle of downloading a segment and the segment is not going to finish in time. In that case, it can signal to the player that we need to try to get the segment at a lower bit rate in order to avoid stalling. And that we'll see, that's the player's abandon rule. And that we're going to see just a second with some of the examples.
So yeah, we're gonna look at how the different rules are applied in two of the most popular JavaScript players. So we're gonna look at how some examples from HLS.js and Dash.js. So for those who don't know them, HLS.js and Dash.js are the main HTML5 media engine today used to play Dash and HLS. And actually most of the commercial players use these media engines under the hood. So both of the media engines have several ABR rules, most of the time 2 main ones and 2 secondary ones that are tied to some constraints. So to give a first example of the player size capping, here's how it works with HLS.js. So every 1 second, HLS.js checks the player size and compares it to the different bit rates available, and just basically removes all the bit rates that are bigger, where the resolution is bigger than the actual player size. And it removes it from the list of selectionable bit rates by the ABR algorithm. And of course, this check is dynamic, and so if you go into to full screen, if you change the player size, it will update this list of available bit rates, so you can go back to a bigger bit rates if you go into full screen. To illustrate the drop frames constraint, here again is a rule from HLS.js. So HLS.js actually looks into an API provided by the browser that gives you the number of dropped frames since the beginning of the playback. And so it counts these drop frames and calculates a ratio which is the number of drop frames by the number of decoded frames. And if this ratio is bigger than a certain threshold, which is by default, I think 20%, it will directly take the level, the bitrate that is played, and basically ban it from the list of available bitrates, because it considers that your CPU, your device doesn't have enough power to decrypt this level, and so it will switch down to a bitrate that is lower. And so, yeah, this threshold, of course, can be modified in the configuration options if you want to make it bigger or lower. So now let's look at the startup strategy in both Dash.js and HLS.js. So with Dash.js, it's quite simple. It has one main rule that says that whenever the buffer is empty, you will always download the lowest bitrate, the lowest quality. And of course, when the video starts, the buffer first is empty, so it will always start with the lowest bitrate and then switch up to bigger bitrates after the first segment. In HLS.js, it's actually not like that. It will not try to download the lowest bitrate first. It will just download the first bitrate listed in the HLS playlist, and most of the time it's the median bitrate and not the lowest one. But it still applies the the player size capping rule. So if your player size at the beginning is small, it will still download the smallest bitrate that is compatible with the player size. So now let's see how the main bandwidth estimation algorithm works with HLS-JS. So at each new segment, it will estimate the bandwidth by looking at the latest downloaded segment and will divide basically its size by its download time. Then it will apply a smoothing function, which here is a combination of a slow and fast exponential weighted moved average that Erica will talk about a little later in the example with Dailymotion. And so to this smoothed bandwidth estimation, there is another adjustment that is applied, which is a multiplicative coefficient, which is 0.7 when you try to go up and 0.8 if you try to switch down. And so this has two main effects. The first is because the bandwidth can be easily overestimated. Having a smaller coefficient than 1 basically avoids going up too often and to overestimate the bandwidth. And secondly, with having a different factor where switching up and switching down also makes it more easier than to switch down than to switch up. That also reduces basically the number of oscillations of the bitrate. So now let's see as a bonus what happens when we add another way to download the segments. So with StreamRoute, we basically get individual segments from multiple sources, either from the traditional CDN or the server, or a network of peers. And because players are not used to this kind of multi-sourcing, we need to assemble and store segments before actually handling them to the classic media buffer. And so these prefetched segments from other peers are stored in what we call a peer-to-peer cache. And so when the media buffer requests a new segment, instead of asking directly from the CDN, it checks first if the segment is already present in the peer-to-peer cache. And if it's not, it still can just get it from the CDN. But if it is, it gets the segment almost instantaneously from the peer-to-peer buffer. And in that case, the player will see the estimated bandwidth as almost infinite. And in that case, of course, it wouldn't work with the bandwidth estimation algorithm we just saw before. So to avoid that, we have introduced a new metric that calculates the average peer-to-peer bitrate, which is, to simplify, the average of the download speeds from the other peers that contributed to getting the segment. And as the peer connections are made with people who are on the same ISP and in the same city, and the WebRTC protocol we're using is much more efficient than the classic TCP HTTP stack. Often the bandwidth is higher than the CDN bandwidth, which allows users to download and play higher bitrates than with just a CDN-only approach. So we have covered the main ABR bandwidth rules, but a lot of the media engines have actually additional rules to handle certain edge cases. So for instance, here the fragment abort rule is very useful in case of sudden bandwidth drops in the middle of a segment download. And it's present in both HLS.js and Dash.js. So in HLS.js, during the segment download, this rule checks the estimated time when the segment download should finish, and it will compare it to the estimated time of the buffer starvation. And so if the time to buffer starvation is closer, if it's lower, it tries to see if there is another lower quality that could avoid that. And if it is the case, it will abandon the request for the bigger segment and try to directly load a smaller bitrate to avoid buffer starvation in that case. In Dash.js, it's a bit simpler, actually. It just compares the estimated download time of the segment with the segment duration. And if it's bigger than, I think, 1.5 times the segment duration, it cancels the request and requests a new quality based on the bandwidth information it got from downloading this aborted segment. And so just like with HLS.js, this rule is, of course, used only after a certain time, like not in the first seconds of the segment download, to avoid aborting segments too early when you didn't basically just have the time to estimate if you will download the segment in time or not. So this rule is especially important when you have very big segments, which is often the case with HLS, who has like 10-second segments. And to finish, I wanted to show you an additional rule here in Dash.js that is based on the buffer estimation, and that will make a good transition with the next section. So in Dash.js, basically there is a rule called buffer occupancy rule. And this rule acts as a counter to the bandwidth estimation rule when this bandwidth estimation tells the player to switch down. Basically, it says that if the buffer size is bigger than a certain threshold, you should stay on the same quality because you have enough buffered video to not worry about the bandwidth drop for now. And so this rule is particularly useful for VOD use cases where you may have many segments buffered into your buffer in advance. So yeah, as we saw in section 2, bandwidth estimation is not an exact science and can have several pitfalls, including too much oscillation, lack of resiliency, frequent network fluctuation, etc., etc. And so we might wonder if bandwidth estimation is so difficult, uncertain, and error-prone. What if we build an adaptive bitrate algorithm that is not using bandwidth at all into account? And actually, it's possible, and a good parameter to replace the bandwidth for the estimation in that case is actually the buffer itself, so the buffer size. And so some people looked into that and actually found out that it's working pretty well. So how does it work? For buffer-based algorithms, basically, they're based on the estimation of the buffer size and also how quickly it is filled or how quickly it is emptied. And so the basic approach is to say that if we want to avoid buffering, we should always fill the buffer faster than it empties, basically, than it plays. And so as the buffer fills up, and get close to a maximum level that we're defining, that here is Bmax, basically, we can switch the bitrate up and try to add bigger segments. And if even with adding bigger segments, the buffer is still filling up, meaning that it's filling up faster than in the video plays, than it empties. So it means that we can switch up and up and up until reaching the biggest bitrate. And in the case, at some point, if the buffer starts basically emptying faster than it fills up, it means that we need to switch the quality down, the bitrate down. And so a lot of research and actually production tests have shown that this approach works a lot better than the bandwidth one, as long as you have enough, a big enough buffer to begin with. So when I say big enough, it's around 90 seconds, so like 1 minute and a half. So it works very good for long VOD streams. And so by design, it doesn't try to estimate the bandwidth, so it's a lot more resilient to bandwidth changes, and it performs a lot better for the rebuffering rates. But the buffer-based only algorithms are not perfect and have some flaws too. So first, such an algorithm is too conservative in the startup phase because it will download the lowest bitrate for like dozens of seconds. It can download the lowest bitrate for 1 minute because it needs to fill the buffer up before going up into bitrates. Which is not perfect at all because people want to have a higher bitrate directly. Also, another side effect is if you have chunks of different size, so when we have VBR, so variable bitrates, and if you have a segment of 2 seconds that sometimes can wait like 4 megabytes and sometimes it can wait 8 megabytes, in this buffer calculation approach, it can basically do some errors in this algorithm. So it's better when you have a bitrate that is not too variable. And finally, and that's of course the biggest caveat, is that if you're doing short videos or very low latency streaming, you just don't have enough segments in the playlist to get to the maximum value of the buffer. And in this case, the buffer-based approach won't work very well because it won't be reactive enough to the buffer size changes, and will, of course, be suboptimal in terms of average bit rates. So to mitigate that, a good approach is to have a hybrid algorithm between the buffer-based and the bandwidth-based one. And basically, in that case, during the startup time and the ramp-up phase at the beginning of the video, you will use bandwidth estimates to get to the maximum bitrate very quickly. And once you reach a good size of your buffer, you can switch to the buffer-based algorithm to minimize rebuffering. And of course, if your playlist is too short, or if you're doing live with less than 20 seconds, in that case, you just always stay in this startup phase where you're using only the bandwidth approach, the bandwidth-based approach, with some control with the buffer, but the main algorithm remains the bandwidth estimation for live. And so, if you want to look into an example of this buffer-based approach, Dash.js implemented an algorithm called BOLA. You can see the code if you go through this link, and they also published a research paper on that. I won't go into detail, but basically it uses this buffer-based approach with a utility theory where they maximize a function. Basically, they maximize the possible bitrate, and they minimize at the same time the risk of rebuffering with a coefficient that you can change to see if you want if like the maximum bitrate is more important for you, or if the risk of rebuffering is more important for you. And so I'll let Erika to present the real results in real world with Dailymotion.
Okay. So does any of this actually really matter? It turns out that yes. To give you an idea of how these algorithms can actually have a pretty big effect in production, we have some customer data from Dailymotion. Just to give you a little bit of background on Dailymotion, one of the largest video hosting platforms in the world. They have over 100 million video views per day, and most of their users are today using HTML5, over 3/4, and that's where they wanted to do the improvements. So the experiment that they did was actually inspired from our presentation last year. We gave a very similar presentation here at Streaming Media East last year, and that kind of inspired them to do some tweaking of their ABR algorithms of HLS.js, which is the player that they built and are using. So in the beginning, before the experiment, HLS.js had a relatively simple bandwidth estimation algorithm. We basically took the last couple segments of history and applied a coefficient to get to the next bit rate. So there was no type of smoothing or anything like that. So that's what they wanted to play with in this experiment. They wanted to see if by applying a smoothing function and trying to take more history into account, it would allow them to have less rebuffering and kind of improve the algorithm in general. So that's what they decided to do, was kind of add the smoothing element. They were inspired also by Shaka Player. They looked at Google's Shaka Player to see what algorithm that Shaka Player was using, and basically chose the same average, which is the exponential weighted moving average. This is an interesting average because it takes into account all historical values, with the most recent ones weighted the most heavily, and then the weight decreasing exponentially. So it takes into account all of history, and with more distant values counting for less and less. So the interesting thing about Shaka Player's algorithm, and this is where they really experimented and tweaked, was Shaka Player actually used two versions of the two averages, exponential weighted moving averages. One quote unquote slow average that allowed us to switch up to a higher bit rate very, very gradually, and one faster algorithm that allowed us to switch down to a lower bit rate very, very quickly. So the tricky part for this was that Shaka decided to weigh the last three segments very heavily for this fast algorithm, to say that they basically use this magic number of three segments to weight very, very heavily if we wanted to switch down. And then they wanted to use 10 segments if we wanted to take 10 segments of history and weight them much more heavily if we were doing the slow algorithm and moving up. So what Dailymotion wanted to do is see if these numbers would actually work for them in production as well as it did for Shaka, or if they were going to actually take into account more seconds of history for the faster one or fewer, et cetera, et cetera. So they played with these numbers a little bit and had some interesting results. So here are the numbers before the optimization. So here we're looking at rebuffering percentiles. So the number of streams that had 0 rebuffering events, 1 rebuffering event, 2, et cetera, et cetera. And as a disclaimer, this was basically for their traffic all over the entire world. So the rebuffering rates are obviously much lower for Europe and the US, but this takes into account that they have videos in every country of the world, and some in countries of the world where there are significant connectivity issues. So at least what we see here is that actually HLS.js, their HTML5 player, was actually underperforming FlashLS, which was the kind of ubiquitous Flash player for HLS. Pretty significantly, by 8% essentially, before they made any changes to their algorithm. After the changes were actually made, we see that they were actually able to increase the number of streams with 0 rebuffering incidents by 9%, or 9 percentage points essentially, when they tweaked their algorithm and started using the exponential weighted moving average. So what they found was that their average worked best when they took 9 seconds of history for the fast algorithm and 3 seconds of history, or for the slow algorithm and 3 seconds of history for the faster algorithm. So it's slightly different than what Shaka had, slightly different use case. And we're able to basically increase the number of streams with 0 rebuffering events by 9%, just in a couple weeks of testing. And so that's really significant for just tweaking, a couple metrics on their player. That's not something that you could accomplish by changing CDNs or doing a lot of other things. So that's quite significant. However, you could say, OK, great, rebuffering. We have fewer rebuffering events. But how about all of the other QoS metrics? Are we breaking any of those? Fortunately, what Dailymotion found was that with this change, the number of track switches also decreased quite significantly. And we didn't actually put it on the slide, but the bit rate was essentially maintained slightly higher as well with these. The average bit rate was slightly higher with these changes as well. So to kind of conclude on that, obviously Dailymotion has a wealth of source of data with 100 million views per day. They were able to do this very, very quickly, have great data, and to really make changes quite quickly. Basically took them less than 2 weeks to improve their rebuffering by 9%. Keep in mind, obviously, the numbers and the type of smoothing that you want to do or how you're tweaking this algorithm is obviously going to depend a lot on your use case, including the segment lengths that you have, your bit rates, et cetera, the devices that people are using. So it's, the most important thing here is to have the right workflow, the right A/B testing workflow set up in order to be able to do these experiments and to actually collect the data, and to really understand your use case and make kind of educated hypotheses and guesses as to what is going to help and what is going to harm QoS. You never really know, there are always surprises, but to have a good setup will allow you to do that. So these parameters are actually implemented in production today on Dailymotion, and they're always working on doing a lot of QoS experiments and other tweaking other parameters for constant QoS improvements. So just to kind of finish up pretty quickly, your player's ABR logic is not something to overlook. It's often an overlooked part of the video workflow that has a big impact on quality of service. We can't stress it enough, but the first thing to do if you are going to kind of dive in and try to modify this, your player's ABR logic, is to really understand your use case. What type of streaming? Are you doing live or VOD? What kind of devices you're trying to serve? What regions of the world you're trying to serve as well? Regions, countries, ISPs, everything has a pretty big impact on that. Once you understand what's most important to you, once you understand your viewers and your use case and what's most important to you in terms of that optimization, do we want everyone to be streaming on the highest bit rate possible, or do we absolutely want to avoid rebuffering at all costs? That's a trade-off. You can make a better decision as to what you actually want to play with and want to change. The good news here is that most open source frameworks make it very, very easy to adapt and fine-tune your algorithms. For example, with HLS.js and -js, you can both just tweak the parameters, or you can just completely write your own rules. And we have some links here. We'll be happy to put this on SlideShare as well if you're interested, so you can actually have access to these links. So you have a lot of flexibility and a lot of freedom to really tweak and even write your own rules. Also, many proprietary players offer some flexibility as well, especially with some of the parameters in terms of startup time and player size, et cetera, et cetera. You can have some liberty as to what you want to change. And finally, again, to really be able to do this effectively, Whether you're simply tweaking or if you're actually implementing substantive changes, just make sure you have the workflow in place to effectively test and iterate your solution. Your QoS metrics are a precious source of information, and a good A/B testing strategy can be a really quick and effective way to make concrete changes. So again, everything is quite use case specific. So if you have any questions, any very specific questions, don't hesitate to come up to us after the presentation. And if not, I think we'd be happy to take any general questions now. Yes.
So .js, HLS.js seems to be geared towards browsers.
Mm-hmm.
What about mobile devices, smart TVs, Apple TV, Roku?
Yep. With mobile in general, for the iOS native player, unfortunately, there's a lot less customization possible. Especially, I think with Android, you do have a little bit more customization possibilities. Do you want
Yeah, on Android, if you use Exoplayer, you can also write your own rules or modify the rules that already exist. With iOS, the issue is that you can only use a native player and you can't really access the rules. Apple actually doesn't even give the rules that are used. From what we've seen, it's quite simple, a little too simple, I would say even, than what can be used with HLS.js or Dash.js. With Dailymotion, I think mobile performed like 10 or 50% worse than desktop.
Dailymotion over 60% is desktop, so
Yeah.
for that
Yeah.
large,
Yeah.
if
Yeah.
you do this.
Mm-hmm. Mm-hmm.
How about the TV boxes?
It's the same. They also use native players most of the time. Some of the smart TVs can use HTML5 players, and in that case, you're able to apply those kind of rules too. So it really on smart TVs, it's really case by case. Some of them will provide you a very basic player, and you can't really customize anything, and some of them will let you use HTML5 player of your own.
I have one more question.
Mm-hmm.
On a few occasions, you said that some of the aspects that you discussed are either used or not used in the current production players. How do you know what is out there being used? Is it just trivial to download a JS file and see what the algorithm is? Or is this based on some business partnership or whatever insights you might have?
So how do we know if the algorithms we're talking about are used or not used? I'm just repeating the question for the live. So it's both. We know the code because it's the players that our partners or customers are using. Some of them are open source. In that case, we can just see exactly the algorithms that are used, and we also, of course, talk with them to try to work together to improve the QoS. And so we know what algorithms they're using also from that.
Yes?
So, just a follow-up question. The Dailymotion study that you showed here, was it only for the 60% of the users who did desktop, or did it also include mobile?
So the question is, were the Dailymotion results that we showed only for desktop, or was it mobile as well? And so I believe it would only be desktop.
So the improvement was only on desktop, on the HLS.js player. The mobile stats were also collected, but they stayed the same because they were not able to apply a new algorithm on that.
And just to follow up, the optimal setting in their case, was it 9 seconds and 3 seconds, or 9 segments and 3 seconds? That was not?
It was the parameters. I think it is in seconds. Yeah, but again, you shouldn't like just take it and use it because.
That's why I was wondering, what was the segment duration that they had?
At that point, I think it was around 8 seconds per segment.
So pretty much 1 segment. But then you're coming, if it's 8 seconds per segment and you're having 9 seconds.
Yeah, so
that's the when you are looking at 1 second.
this parameter is a little tricky. It's actually this parameter is Technically, it's the half-life of the exponential moving average, which means that if your this parameter value is like 10, it means that half of the weight of your estimation will be from the segments that were like under 10 seconds, and half of it will be for the segments after 10 seconds. So it's the half-life is not just like a any
other questions? Okay, thanks so much.
All right, thank you.